Okay, so let's settle down so you can get started. Okay, so let's get started on a new topic which will take up almost the rest of the first half of this semester. Plus, we will revisit this again towards the last few lectures as well. Okay, so this is on MIPS. Okay, so MIPS processor is one of the popular architectures being used by manufacturers to design processors. Okay, so in this we're going to learn how a processor behaves, how an instruction, okay, when we fetch from memory, how does it go through the entire processor to get decoded and executed, and how it accesses memory, and how we can also design a processor or improve the performance of the processor using different approaches. Okay, so these are the few things. So when you talk about MIPS processor, a processor itself has a lot of things that we need to look at. We need to understand what are the registers involved, what is the assembly language that we're going to use, okay, and some of the operations regarding the assembly language. Okay, so we're going to look in that step by step. So we have seen this before, where we say that right now when you write your high-level programs in C or in Java or Python or whatever, when you compile, you are actually translating it into assembly language. Okay, so this is actually currently transparent for us. Okay, as long as you're dealing at the high level, this is transparent. Okay, as long as your high-level code is correct, your compiler is compatible with the processor you're working on, then this whole process is transparent and automatic. Okay, and eventually the assembler translates it into machine code. Okay, why? Because your processor only understands ones and zeros. Okay, so eventually we are targeting this. Okay, this is the end game. Okay, so how do we make use of a processor, okay, to do our work? So that is where the instruction set architecture comes in. What is the instruction set architecture? It is basically a middle layer, okay, to interface between the hardware and the software. Okay, when you learn high-level program, you just learn the programming syntax. Okay, so when you write your C program, you do not care too much about what is the underlying hardware. But when you go into assembly language, you must understand the hardware because you're going to write the code that deals directly with the hardware. So you must have this understanding of the hardware, and that is where the instruction set architecture comes in. Okay, so what does the instruction set architecture give you? It gives you everything you need to know, okay, to make the code work correctly. Okay, in terms of registers that are available in the processor, what kind of instructions this processor can execute, okay, and also when you want to design your hardware system around this processor, how do you do it? Okay, so that is the main idea. So the whole idea behind this is when you know your architecture, you are able to write efficient code, okay, that works directly on your hardware, and you're also able to design multiple variations of a processor based on the same architecture. So we say that your machine code is the one that your computer or your processor understands. But to write your instruction in just ones and zeros is not practical. Of course, that's how they all started, correct? If you do some history search on your first generation of computers, okay, many years ago, that's how they did, correct? Using vacuum tubes. Okay, and then they key in ones and zeros, and then they try to execute a program. Okay, so of course we have progressed a lot from there. And what does assembly language give us? It gives us an intermediate step. Okay, so this ones and zeros is actually to do a, for example, add instruction. Okay, but to write these ones and zeros every time to do add instruction is not practical, alright? So that is where the assembly language comes in. So the assembly language gives us a sort of middle level instruction that relates to the hardware that you have. Okay, what is the hardware? We will look at that now, okay, the registers that you have. So let's look at this example to better understand where this whole thing comes into place. So this kind of a C code is what we have been writing all over. So you have a for loop. So in this for loop, what do you have? You have two variables, I and result here. So when you say you have two variables, what does that mean? That means that you have set aside two memory locations to hold this data, correct? Okay, and I'm doing some computation, some algorithm based on these two variables that I have. When I say compile, okay, when I click on the compile button, it needs to get translated. That means from C code, I need to translate it into assembly code. Okay, so this is, again, the double code is there intentionally. Your actual assembly code doesn't look like this, but we're just trying to give you the steps. So the steps is what? I need to do a result variable add with I, put back into result, increment my I, and put back into 1, and I check for the condition whether to repeat this loop or not. Okay, so effectively, I have 3 steps to do. Okay, so let's see what happens at the hardware level. At the hardware level, you have your processor, okay, in this case, the MIPS processor, and you have memory. And the connection between your processor and all your devices is what? All your electrical or electronic wiring, correct? Okay, so in essence, you have actually 2 buses. Okay, one is called your address bus, okay, and the other is called data bus. Okay, so effectively, you have 2 main buses plus you have additional control lines. So there are still additional control lines here that will link up your processor to your memory and so on. Okay, of course, we're not going to go into the bus and how to design a system based on the address range and things like that. Okay, but roughly this is the main configuration. You have your processor, you have your memory plus your other subsystem, and you have your address bus, data bus, and control signals, okay, to communicate with all your peripheral devices. Your memory is basically there to store your code and to store your data. Okay? For simplicity's sake, we will just think of memory as a single entity for now. But definitely you have multiple memories in one system, correct? You have your permanent storage, you have your volatile storage, then you have your semi-permanent storage and so on. So you have different types of memory technology within one system itself. Okay? But for now, we will just take memory as a single system. Okay, so your code that you compile will generate some memory or occupy some memory space. The variables that you declare in your code will also occupy some memory space. Which part of the memory it goes to, also it makes a big difference depending on how you code. Okay, if you declare your variable as global variable, then it goes somewhere else. If you declare as a local variable, it goes somewhere else. Okay, if you declare as static, it goes somewhere else. Okay, so there are different locations where a variable can be stored in a memory address depending on how you write the code. Okay, so again, these are all the things that you will overlook when you just do high-level code. Okay, but when you look at the processor and you look at memory, then you need to look at all of these things. So effectively, what are you trying to do? Okay, so if you look at this arrow here, I want to execute this instruction. Correct? That is the instruction I want to execute, and in order for me to execute this instruction, I must take these 2 variables, I and result, from my memory, okay, and bring it into my ALU within my processor, correct? Your ALU is what? Your arithmetic and logical unit. Okay, that means that is the component in your processor that is eventually doing all the computational work for you. Okay, so in order for me to do this one instruction, I need to do 3 things. First, I need to get the result variable into my processor. I need to get the I variable into my processor, and then I execute the instruction, correct? Okay, so of course, if I keep doing this every time, my whole system will be very, very slow. Okay, why? Because this memory access across the bus is the bottleneck of your system. Okay, every time I need to go outside of my processor to fetch data, I become very slow. Okay, so in order for me to improve the efficiency, okay, to make myself or make the code run more faster, what must I do? I keep the data that I want to access closer to me. So closer to me means what? I store it inside registers. What are registers? Registers are memory locations that are within the processor. Okay, that means once I take a data and put it inside a register, that means it's considered part of my processor. I don't need to go out to fetch the data in again. Okay, so that is why you have registers inside the processors. Okay, so the first step will be you go out, grab the data, keep it in my register, do all my calculation finish. Then when I complete my computation, then the result I write back to my memory. Okay, so that's the whole aim. So what I want to do is, first step is I want to be able to populate my registers with the data that is in the memory. Okay, so what I will do is I will first do this two step here. Load I into R0 and load result into R1. Okay, the names, we will come to that in a while. R0, R1 are just names I'm giving you now. Later, we will look at the actual register name that you have. For now, you take that R0 and R1 are two registers you have in your processor. So what I need to do, I first need to execute two instructions that will take the I data from memory, put into my R0 register, then take the result data and put in my R1 register. Okay, once I complete these two steps, that means I subsequently do not need to go to memory to fetch this data, correct? Because I already have it in my local register. Okay, so that is the first instruction I execute, R0 loaded with I value. And the second instruction is to load from my load result into R1. Okay, so these are two common terms you will see quite often, load and store. So load and store basically mean is you move data between memory and register. Okay, so whenever you say load is from memory to register, when you store is from register back to memory. Okay, so that is the first thing I will do, to load from my register, from my memory into my register. Okay, well after that, then I can straight away do all my computation based on my registers. Okay, so once my data that I need to access is inside my register, I no longer need to deal with memory for a while. Okay, so I just carry on with all my arithmetic operations inside my processor with the data already in the register, so it's very fast. Okay, so in this case, for example, I do it R1 plus R0, put back into R1. Okay, and then I take R0 increment plus 1, put back into R0. So you can see there's two different types of instruction here. In this example, you see two different types of instruction. One is this. This is what? An instruction where you take a register, okay, and a register. Correct? R0 add with R1, correct? So if register add with another register. This instruction is what? Register plus a value, correct? So these are again different type of instruction your processor can execute. So one type is register and register. The other one is register and value. Okay? So all are the different type of instructions your processor can handle. Okay, so I keep on going through the loop until the condition is no longer satisfied. Okay, so the whole process keeps repeating. Okay, once I finish everything, then the last step is what? Is to move back the data from my register back to my memory. Okay, so the two variables which are I and result, okay, you want to update back into my actual memory location. So that is where you need to do the store instruction. Okay, so you need to store R0 into I, and you also need to store your R1 into result, correct? Okay, so these are the last two steps. So the first step and the last step is always a memory access. Okay, the first step is you load from memory all the things you need. You do all the computation with the register, and the last step you write everything back to your memory location. Okay, so this is basically called the load store model. Why? Because you want to minimize memory access as much as possible. Okay, unnecessary memory access will slow down your whole system. Okay. Now, what are registers? Like I said, these are considered fast memories. Okay, so this is a register. and it's just there to hold data for you. Okay, and once you have your data in your register, you can do whatever you want with all the instructions that you have. Okay, so an important concept of register is you do not think of them with any data type. The data type is only what you know. Okay, it's only what you, just like if I declare a float variable, what does the value inside represent? Is it a temperature? Is it a weight? Is it humidity? Whatever. Correct? So when you declare a variable, what is the value inside? How it makes sense to you, only you will know. Same thing over here. A register is nothing more than a 32-bit memory location. You can put data inside, you can manipulate data inside. But what it holds, what it signifies, only you will know. So you do not have to think of it as, is it a character? Is the most significant bit 1? Do I need to check the most significant bit? Only you will know. Correct? Because you are dealing with the data. As far as the register is concerned, it is just a placeholder. Okay, it's just a memory location within the processor to hold data for you while you do your program. There are a total of 32 registers inside your MIPS register, MIPS processor. And you can access them using the number or the name. So the number is 0 to 31. So you can see in MIPS, hexadecimal is denoted by a $sign. Okay, it's denoted by a $sign in front. So you have to be careful depending on what you are doing. In your C programming, you use 0x, correct? Okay, in over here, you use the $sign for your hexadecimal notation. Okay, so your register is names from 0 all the way to 31. Okay, so the register can be accessed either using name or using the number. Both is the same. Okay, what is the use for different type of register, you will see as we go along the way. Okay, but for now, you just take it that there are 32 registers. Register 1 is not mentioned here because it is reserved. Okay, it's reserved for assembler. And register 26 to 27 is also not mentioned here because it is reserved for the operating system. So the rest of the registers are there for you to use. This usage here, okay, you can see that there is some sort of preset usage. This preset usage is followed by who? This preset usage is actually followed by the compiler. Okay, so the compiler, when you just click on compile, the compiler will make use of this preset arrangement to allocate the different registers for the different usage. Okay, some of them you can always play around. Okay, that means, for example, V0, V1, A0 to A3, T0 to T1, you can just interchangeably use when you are writing your own program. Correct? Because when you are writing your own program, you have control over which registers are for what purpose. Okay, let's look at a assembly language code to better understand how we write it. So the first thing is your assembly language code. You can use commands. You can write commands by adding a hex sign. So by adding a hex sign, anything that follows is a command. Okay. Each line of assembly language code only contains one instruction. Okay. So one line is one code. Okay, one instruction. Now let's look at a bit more on this instruction. The general instruction syntax. Why I say general is because there are different variations. Okay, so different instructions will have different format. Okay, so the general syntax is this, where you have 3 registers involved. The first column is your instruction, okay, which is also known as the opcode. The last 2 are your 2 source. Source 1 and source 2, and the first one here is your destination. So in this case, what is the objective? This and this are supposed to perform an add operation, and the result is supposed to go into S0. Okay? So that is the general MIPS instruction syntax. Okay? So this kind of instruction where you have 3 registers involved, the 3 registers basically have 2 of them which are source and 1 of them which is a destination. Okay? So that is the effective result that you get. Okay, so if I try to relate this assembly language code to my C code, how does it look like? So in a C statement, when I do an add operation like this, I need to say in MIPS assembly language code that I want to do an add operation. And then I need to add the two registers together, put the answer into S0. But this is just the add operation, correct? What must I have done before this add operation? I must have transferred my data in B and C to S1 and S2, correct? Okay, so this is just the add instruction. So prior to this, I must have done the transfer of data from my variable in memory to my register, correct? Then I perform the operation and then I can write back to the memory location. Okay, so there's still a pre and a post to this. Okay, so again, most instructions are register to register, but we are also going to look at some instructions that can be registered to memory and memory to register, okay, which are the load and store, which we saw earlier. How about this? Again, this is called a subtract instruction. Again, S1 and S2, subtract, and the answer put into S0. So in subtraction, of course, the order is important, correct? If not, you will get the opposite sign when you do a subtraction. Okay, so how do I do this? You have three variables, okay, and you want to do an operation. How will I do this in MIPS? So in MIPS, you can only have two source and one destination, correct? In every instruction. So this is not possible in a single instruction. So you need to break it up into multiple instructions. Okay, so such an operation, you need to break it up into two separate instructions. So I can say I do this first, and then this result I subtract D. Okay, so for example here I say S1 plus S2 put into T0, and then T0 subtract from S3. Then the result go into S0. Okay, so you need to break up your instruction to multiple MIPS assembly language instructions if it's complicated. Similar over here, you again need to break it up into multiple instructions. Okay, so G plus H is one result, this is another result. Okay, so of course these are temporary results, so you can consider using T0 and T1. If you use any other general purpose register also is fine. It's fine, your answer will still be correct. Okay, so this is how the translation will be done. Okay, similar to this. Okay, so I have 4 variables to add, so I need to do 2 by 2. Okay, so I have total of 3 instructions. This one again, I need to do a subtraction followed by addition. Okay, so the syntax, don't worry, as you do a few examples, you'll get used to the syntax. Okay, so just now in the first example, like I mentioned, that we saw 2 different types of instructions. One was register to register, the other one was register and value. Okay, so this value is called immediate value. Okay, so we call it immediate value. Why? Because that value is already specified in the instruction. Okay, so the difference is what? Previously we say is add. Okay, all these are add instruction. That means it's register and register. When I have an immediate, is add I. You must remember to add the I in the end. So when the processor sees that it's an add I instruction, it is expecting what? It's expecting one register and one value. Correct? It's expecting one register and one value. So this is the register. I add with this value, and then the answer I put back inside here. Okay, so the immediate value, what is the range I can specify? Okay, I can specify a total of 16 bits for my immediate value. Okay, and the 16 bits is in the range of this. Why? Because we are following the 2's complement number system, correct? Okay, so it is 2 to the power of minus 15 to 2 to the power of minus 15 minus 1. Okay, so let me stop this here for a while and open up this. I I just uploaded a while ago into IEEE. So this is your MIPS instruction reference sheet, which you will need for your midterm, for your exam, and so on. So if your eyesight is poor, please bring along a magnifying glass. Okay? So this gives you what? This gives you the full range of instruction that your processor support. Okay? Do you need to memorize all of this? Yes. No. Just kidding. Hopefully I wake up some of you. Okay? So you do not need to memorize. So it's either you print out and you bring, or I will print out and attach to your exam and midterm sheet. Don't worry. So how do I decode this? Okay, so for example, I look at this. Okay, let me zoom in a bit. So if I look at this add instruction, for example, is add, and I have RS, RT go into RD. Okay, what is RS, RT, RD? We will look at that in a while. Okay, and what is opcode? We will look at that in a while. Okay, what you can see here is this. These are all the registers you have. Okay, so the register names, the numbers are all given, plus the full range of instructions are given. Okay, so you can see that for add instruction, I have two registers, RS and RT. If I do a add I, it is considered an I immediate instruction. So I have RS, which is a register, plus the immediate value. Okay, so as you learn more and more instructions and you learn the format of the instruction, then you will learn how to appreciate and decode this a bit better. Okay, but everything is inside here. So all the instruction that your processor support is actually mentioned in this data sheet here. Okay, so let's carry on first. So the register 0 is very often used in the code, correct? Because many times when we do a loop, for example, you will say I equals to 0. Or we do a compare whether it's equal to 0 or less than 0. So since it is very regularly used, one of the register is also called register 0, okay, which is number 0, or you can also say $0. Now, what is the purpose of this? For example, if I want to do an assign statement, f equals to g, that means I take the value of g, put into f. Okay, there is no actual copy instruction. So what you need to do, if assuming that g is inside S1, I say g add with 0, put back inside f. Okay, so a copy instruction actually does not exist, but then you can add with 0 and put into another register. Okay, that is how you do a copy. But of course, this doesn't seem so nice to do every time, correct? So what does MIPS do? They also provide you with what is known as pseudo-instruction. Okay, what is pseudo-instruction? Pseudo-instruction means that it is not the actual instruction that will be executed by the processor. When you are compiling your code, it will still translate a pseudo-instruction to actual MIPS instruction. Okay, it will still translate the actual MIPS instruction. Only thing is because these are frequently used, they try to give you a shortcut, okay, to do it. So I can still do S1 copy to S0, okay, by using the move pseudo instruction. Okay, so as I mentioned, the registers, you have a total of 32 registers, and each of it is 32-bit long. Okay, think of it as just 32-bit data. Okay, what it interprets to or what it represents, you will know. Which also means that I can perform any form of data manipulation on this 32-bit data. Okay, so what are some of the logical operations you can do? You can do shift left, shift right, bitwise AND, or not. So this truth table, you should know. So your AND logic is what? As long as any one input is 0, the output will be 0. Only when everything is 1, the output is a 1, correct? Okay, so for AND gate, okay, as long as any one of the input is 0, then the output is 0. Only when all the input is 1, the output is a 1. For OR gate is what? As long as you have 1 in the input, then the output will become a 1. Alright? The NOR is what? The NOR is the complement of this. Alright? The NOR is the complement of the OR. And exclusive OR is what? As long as the two inputs are different, then the output is a 1. Okay, so these are the main logical operation that you will frequently use in your code. Okay, so some of the examples of your logical operations. So shift left logical. Shift left logical basically means you shift the data left by a certain number of bits. Okay, how do I specify that? I say SLL, T2, S0, S4. That means what? That means S0 shift left by 4 and the answer go to T2. Okay, S0 shift left by 4, answer go to T2. Okay, so you can always check back. So for example, if I open up this document, I go and find for shift left. Okay, so you can see shift left logical here. Okay, your RT shift left by a certain shift amount, and that goes into my destination register. Okay, so you can see that you are dealing with one register and one value, correct? Okay, one register, one value, and the answer go back to another register. Okay, RD, RS, RT, we will revisit that again when we look at the instruction format.
V2 is for spin now.
Sorry?
Spin.
Yeah, it's for your lab. For your lab. Okay, so after I shift left, basically means what? That means the most significant 4 bits will be gone, correct? Will be shifted out. Okay, so when I shift left by 4, this most significant 4 bits here will be discarded. And what is shifted in? What is shifted in is all zeros, correct? Okay, so in the end, what you get is this. Okay, so that is how your shift left logical works. Similarly, for your shift right logical, okay, you can shift right by a certain number of bits and pad it with zeros. Okay, why is shift left and shift right very important and useful? Because your shift right and shift left is equivalent to multiply and divide by 2 to the power of n. Okay? When I say this statement here, okay, when I execute this statement, when I say multiply by 8, multiply by 8 is equivalent to what? 8 is 2 to the power of 3, correct? Okay, which means it is equivalent to shifting left by 3 bits. Okay, shifting left by 3 bits. So that is why if I shift left by 3 bits and I write it back, I get the same answer. Okay, same thing if I shift right. Now the question comes, why do I do shift left and shift right if I already have a multiplier? Why do I still want to do this? Anybody want to guess? Why do I still want to do shift left or shift right if my processor got a multiply instruction, for example? Why don't I straight away do? Sorry?
It's cheaper to shift.
Cheaper as in what?
Fewer cycles required to.
Okay, let me see if I have the data. Okay, so this is a summarized data sheet. In the actual data sheet, okay, you will have information on the number of clock cycles the processor takes to execute a particular instruction. Okay, so a multiply or a divide operation will take a lot more clock cycles compared to a shift operation. Okay, so even though you fulfill the same objective, you can do it much faster by using a shift left or shift right operation. Okay, so the compiler will always try to optimize that for you. Okay, can I replace a multiply and divide with the equivalent shift instruction, okay, to cut down on my clock cycles. Next, you have your bitwise AND or not. Okay, why do you need bitwise AND? Because you want to focus on certain number of bits. Okay, so if I want to only focus on this group of bits here, what do? I create a mask. And a mask is what? The bits that I want to keep, I put a 1, and the ones that are not interested, I put a 0. So that's why you see only a 1 in this range of bits here. Okay, and the rest are all zeros. So what is the outcome? The outcome is the result only has those bits from the original data copied over. The rest of the data from the original bit stream is cleared to 0. Okay, so N is used for masking operation. Okay, so depending on what is the data you want to look at and what is the bits you want to discard or ignore. Okay, so for example, if I want to look at the last 12 bits of this word, then I create a mask that has only the last 12 bits set to 1. Then the end result is this. So for AND instruction, you also have an equivalent AND-I instruction. Okay, so you can straight away do an AND operation by specifying the mask. Similarly, for OR, the OR is to do what? Is to set the bits that you want. Because when I OR with a 1, the output will always be a 1. Okay, so when I OR with a, for example, the last 12 bits here are 1. In the resulting bit stream, the last 12 bits are straight away set to 1, correct? But the other bits are kept as it originally was. So again, OR and AND are useful depending on the bits that you want to focus on. Okay, this plays an important part when you're dealing with registers. Why? Because when you have a register, okay, when you have a register with all the bits and so on, okay, right now we are still looking at register as a 32-bit data which represents some data, some information. But you can also look at it as 32 bits representing 32 different information, correct? Why? Because each bit could represent something. Okay? So maybe each bit is to tell you whether any particular sensor in the system was triggered. Correct? So I can say, I always want to look at sensor number 5. Was it triggered or not triggered? Correct? Then I create a mask, just look at sensor 5, whether it's 1 or 0. Okay? So the 32-bit, again, the interpretation is only up to us to define. Similarly for NOR, okay, how we can use NOR to create instructions here. Okay, so how do we get a NOT operation? A NOT operation is to NOR with 0. Okay, a NOT operation is to NOR with 0, you get a NOT. NOT is to do the inversion. Okay, NOT is equivalent to 1's complement, correct? 1 becomes 0, 0 becomes 1. Okay, so why do we not have a separate NOT instruction? Again, the design is always try to be as simple as possible. Okay, minimalist design. So if we know that we can solve the problem using what we already have, we do not create new hardware or new additional overheads to the system. Okay, so that is why you can see that, for example, in your tutorial, when you say you add, when you do subtract, why is a subtraction equivalent to the addition of the complement? Okay, why? Because the addition block is already there for you. Correct? So since I already have an adder block inside my ALU unit, I just make use of that to get the answer. Okay, if I have another subtractor block, it's additional hardware for my processor. Okay, so we try to minimize all of that. Okay, keep the instruction set small, keep the hardware simple. That's the main aim. Okay, exclusive OR. Okay, is to also get a, you can also do a NOT operation using exclusive OR over here. So T0, exclusive OR with T2 put back in T0, you can also get a NOT operation, okay, an inversion operation. Okay, so again, these are some of the things for you to think about. We will let you think about it before we discuss. Okay, so let's look at this. We say that the constant value, the immediate value that we specify in the instruction is 16-bit. Okay, instruction is 16-bit. Okay, so where do I see this? Where do I see this? Let's look back at the instruction here. Okay, so there are 3 types of instruction. So the J we haven't looked at it yet, but we are currently looking at RS and R and I. So R instruction is the instruction where you have 3 registers, 2 with the source and 1 with the destination. Okay, that is the type of instruction where you say add R0, R1, R2, for example. Correct? 3 registers, 2 is the source, 1 is the destination. The other type of instruction that we look at is the one with the immediate value. Correct? And the one with the immediate value is you have 1 register, add or subtract or whatever with the immediate value and store into the final register here. So currently we have looked at 2 different types of instruction, R instruction and I instruction. Okay, so R instruction is 3 register, 2 source, 1 destination. I instruction is 1 source, 1 immediate and 1 destination. So the immediate value you can see here is 16 bits. And just now what we said, the immediate value is 2 to the power minus 15 to 2 to the power minus 15 minus 1, correct? Because it's 16-bit 2's complement representation here, this immediate value. But we know that all our registers here are 32-bit, correct? All our registers here are 32-bit. Okay? So how do I load a 32-bit value into a 32-bit register when I only have 16-bit to specify my immediate value? Can you see the problem? Okay? I want to my register here is 32-bit. Okay? Total is 32 bits here. But my load instructions, only I can load the last 16-bit, correct? Okay? So how am I going to load a 32-bit value into a 32-bit register when my immediate instruction can only hold 16-bit? Okay? So to do that, I must do two steps. Okay? First, I must say load upper immediate. Load upper immediate, what will it do? It will load the upper 16-bit. Okay, so when I have a 32-bit value and I want to load it to my register, I need to break that 32-bit data into 16-bit and 16-bit. Okay, and then I load the upper 16 bits first using the LUI instruction, load upper immediate. And then I do a OR, okay, with the lower 16-bit. Why? Because when I do a OR with a 0, nothing happens, correct? OR with 1, only I force it to become 1. OR with 0, the original data will still be retained. Correct? So I do a OR with the data that I want. Okay, so the whole aim is what? The actual data I want to put in my register is this AAAA, F0, F0. Okay, but I cannot put a 32-bit data inside my instruction because my immediate instruction can only hold 16-bit data. Alright, so I must break it up. So the upper 16-bit, I must use the LUI instruction. Okay, to load the upper 16-bit first, then the lower 16 bits are 0. Subsequently, the OR instruction is to load the lower 16 bits. Then this whole actual data that I want comes in to my register. Okay, so this is a two-step process in order to load your register with your full data here. So these are some of the instruction sets, instructions that are available inside your MIPS processor. You will start to play around with some of this along the way in the tutorial and the labs. Okay, so before we end, let's have a Kahoot quiz. Okay, so again, do not be too worried about the instruction set and so on. We are now only starting off. Okay, in the next few lectures, you will learn more on the instruction, more on the different type of format of the instruction and how you can write your code. Okay, so do not be too concerned. So I still have yesterday's price, nobody claim. The smiley face yesterday never claimed. Okay, so we have to start already because of time. Anybody else? Anybody else? Okay, 4 questions, huh? And so it's an easy quiz, huh? This one you get wrong means you sure sleeping in the class only. Confirm one. Alamak. What, 15, 17 of you sleeping in the class? See? So there are a total of what? 32 register in the MIPS processor, correct? I said that a few times already. Okay, 0 to 31. Okay, either the name or the number you can use to specify. Okay, so there shouldn't be any confusion about this, huh? This one also should be quite easy, right? Okay, so when you have 3 register, this is your source 1, source 2, and this is your destination, correct? Okay, don't get confused, huh? So don't think that the first 2 is source. The last 2 is the 2 source. The first one is actually the destination. Okay, so it's S1 plus S2 stored into S0. Okay? Okay, so most of you get it right. How many bits are available to specify the immediate value for I-type instruction? Okay, so as we saw just now, I-type, you have 16 bit to specify the immediate value. Okay? So that is the maximum. So even if you want to specify a 8-bit value, you still have to specify it as 16-bit because that is the format of the instruction. Okay? Okay, the last question. Each register can hold how many bits? You have 32 register and each register can hold 32 bits. Correct? Don't need to be confused. So in your midterm, you got MCQ, don't know anything, just say 32. Most likely you're very correct. Correct? 32 register, each register 32 bit one. Can? No need to be confused one. Okay, so each register can hold 32 bit of data. All the registers. Okay, can? Okay, so I will see you all next week and you will carry on with the MIPS processor. Thank you. Hey, I must show you the result. Sorry. Winner, streetcar. Who is streetcar? Come, come, come. Lee Hsien Loong in second. Thank you, thank you.
How different is MIPS from x86?
They are all very different architectures.
I believe x86 has no instructions, has move instructions.
Yeah, I mean every processor is designed differently. So some have there's I would say different approach depending on the nature of the
Most of it.
depend on the easiest way to manipulate and communicate the So from the on to go to on. So you need to have an operation because for on to on so basically it's the hardware based where this design I already get easily get so I guess maximize
But theoretically, you can use more of them to create all the logic operations.
True.
But you still have N and all.
It all depends on the hardware cost involved, right? Yes.
Because they appealed to actually then this person because that they are this timing.
He's one of the TAs lah.
Yeah. Then he told us this timings that we can drop by. But this timings right, check the location. Give us the
complacent thing.
Oh，原来什么是？没有，那是不是从 integer 都是 two complement？
Oh no, okay. For the processor lah, they do it in two's complement.
Oh, like in example, what's that？ 等下没有，他没有关的，然后等一下他这个是高。Maybe he confused.
Two's complement is the
Because he needs to do
standard
that.
lah.
He might put in four. Then what will come? Is it also two complement?
Hello.
Four is different.
Yeah, then how do we compile it? Yesterday, so you say mode D, right? So they will convert it into the integer, so it's in computer system is always in two complement. So then what if I want to output in mode F? Then they will also do. If this one is not mode D lah, if mode F, let's say it's a float, yeah. Then what will happen? Like we need to do the whole IEEE thing, or is it also two complement?
Percentage F, it will probably give you a zero or something.
Why is it a zero?
Because it's not compatible.
Oh,
I mean, percentage F will look for a float variable.
Oh.
But this one, but we put integer, but it's still a char variable.
Char integer can interchange.
Okay, but float will never be. Then when you compile, will become error
It
or.
won't become error.
But it will just output zero. That's all.
Depend on the compiler. Some may output zero, some may output something.
But there isn't the proper
decode it.
compatibility
Yeah.
like with char. So the only compatibility between data type is just char and integer. That's all.
Char integer can interchange. Float and double can interchange.
Oh, that's all. So if float to double is the IEEE thing.
Float and double is actually almost the same. It's just that double use more bits.
Or the 64 rather than. Oh, okay. Oh, you can. Thank you.
This is what you see on negative C.
Maybe not char and integer. No.
No. This one is total.
But then Monday I went for the
Oh yeah. Monday you get from my tutorial, is it? Yeah, because first week we made some internal arrangement.
Monday, you came Monday afternoon. Monday morning is me. Monday morning is me, 9 to 10, right? That one is me.
然后呢，可能我们不用想太多。
Mine is group 1 is Friday 1 later Monday 9 to 10 or Friday 1 to 2. The rest are other days.
Ask right, how come the character and integer can just interchangeably used? Is it because of the ASCII?
Because they are both considered whole numbers.
They are not considered
They are whole numbers.
Oh, their character can convert the whole number.
Because character is still nothing more than 8-bit whole number.
Oh,
Whereas a float, there is decimal involved.
in ASCII form.
I don't know. ASCII is just.
No, it's just integer, no decimal place, but float there's decimal place. So if they convert, then there will be some error. Then what is character?
Because character there's no decimal point, so the 8-bit can be still treated as an 8-bit integer. You can look at it that way.
Okay. Thank you.
When you have this T0 and S0, in the sheet you showed, they have like different names for each derivative. So is it like a fixed name as a variable name?
The names are fixed.
So you cannot use any.
No, you have to use the names that are based on the processor registers that are provided.
So this is like specific to each machine, or is it
Specific to each processor.
processing architecture?
Basically each processor. That means if I use MIPS processor, I have this register. If I use Intel processor, I have different register.
Then when you showed us this example, converting the for loop to the assembly, how come there's nothing to initialize the IE?
Yeah, I mean it's not a total conversion. It's just to show you that the relationship with it.
Okay. Then when we have like some code to do this loading, right,
Yes.
it's added by the assembler.
Yeah, I mean of course when you are writing in C and then you do it, you compile, then the compiler will do it for you. But when you are writing your own code, then these steps you have to do first.
Okay. As in this is assembly, so the compiler will generate this.
Yeah, from C the compiler will generate this for you.
Yeah. And I don't really get the last part you mentioned when you load the. I mean, I understand this, but when there's 32 bits here, right? So when we do the OR, how come it's comparing with the first 16?
Because you only specify the lower 16 bits.
But I mean, here we have specified that the whole.
Correct, the whole T0 is all with a new value, correct? But the new value, you're only specifying the lower 16 bit. And the lower 16 bits are already 0 originally, correct? So when I OR with the 0, nothing changes. So the new data gets copied to the result.
Okay.
What's the hexadecimal? Yeah, what's the operation?
The operation is basically, technically it is looking at odd number of ones in the input. So if I have an odd number of ones in the input, I'll put 1. So it generally for 2 input system, then 1 is odd, correct?
Yeah.
So that's why we say 0, 1 or 1, 0 is 1. This one is even number 0 or 2, so the output is 0.
Oh, okay, so whenever is 0 or 2 will be 0, then when it's odd, then it's 1.
Odd number of ones.